All right. Hello, everyone that is watching from the recording. This is 133A final review session for winter of 22. So today we will be going over Lorenzelli's final from winter 2021. So problem one, assume xi, yi for I is equal to 1, comma 2, dot, 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 all the way to n are data points. We have x equals xn, and y is also a matrix, right? So what we want to do in this problem is find analytic for line of best fit, right? So does anyone know the equation for best fit line? How would you approach this problem? Okay, I guess if no one knows, then I'll go through what I did on this problem. Okay, so for least squares, what we have is this equation. A transpose, let me change color. All right, blue. A transpose A, x equals A transpose B, right? And so to find the line of best fit, so basically, actually, let me go back. Okay, so we have the equation ax equals b, right? And we're trying to find the x that best fits this. So, we know what we can do is we have this pseudo inverse idea, right? Where we can multiply both sides by A transpose and then take the inverse. So x is equal to right. Does this idea make sense to everyone? Type yes in the chat if it does. Okay, cool. So we have this. And so we wish to find coefficients, right? So we can denote x, right? By two coefficient a comma b. Maybe this is this confusing? Okay, we'll say we'll just use this notation. So we have our x is equal to a comma b, right? And what we have is, so our x is our x matrix, right? So our my bad. See, where was I? All right, these are data points. Okay, so these are just numbers. So what we have is like something that looks like this. So let's visualize real quick. X, Y, and then we have these data points here, right? So this right here is xi, comma yi, right? So yeah. So what we can do from here is that we can say that A comma B is equal to our X matrix, right? Transpose X, right? Y, right? Because what we have is, let's see. Let's call this Q, right? So what Q is right. So what Q describes is A and B, right? So they're constants such that you know A X plus B is equal to Y, right? So that's kind of what the idea is. So basically we can organize this into a matrix, right? So actually let me rewrite this. So okay, let me define on the side. Let me define on the side X prime is equal to X and then 1, right? So I'm gonna write this one as a like fancy. So this will just denote the column vector of all ones, right? So yeah. So we can write this equation as X tilde AB equals Y, right? Does this make sense to everyone? Sorry, I was a little rambly in my explanation. Okay. All right. People seem to understand. Okay, so let me scroll down. All right. So now we have this equation, right? Now we got to find the best fit line. So to do this, we write x tilde inverse, x tilde transpose times x tilde, and then we take the inverse of that, right? And then x tilde transpose y, right? To get a comma b, right? So this gives us the coefficients. And now what we want to do is just do some math. Which do you want to see me do the computations or should I just give you the final result? Type a final result in the chat if you just want me to write down the final result of the computation. Computations would help? Okay, I will do the computations then. All right. So since I'll do the computations, I will do them in yellow. So we're using mostly blue and yellow today to represent UCLA, of course. Okay, so all right, AB is equal to x1, x2, dot, 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 xn. And then this is all stuff 1, right? Transpose x1, x2, dot, 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 xn, 1, wait. All right. So we're going to have to matrix multiply some stuff. So, okay, first, let us compute this. When we compute this, you know, we do row times column. So let me rewrite this so it's a little bit more visually pleasing. x1, comma, xn, 1, 1. Right. And we see row times column, right? we get x1 times x1, x2 times x2, blah, 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 and we add them all up. So we get this matrix. This is our matrix element here, right? And then let's do another multiplication. So first row times second column, right? We get summation of I equals 1 and of xi, right? And then we have the same thing, right? By symmetry, we can see that we have the same exact thing for the second column times the first row. And then we can see that, the one vector dotted with itself is just the length of the vector itself. So does this computation make sense to everyone? Type yes in the chat if it makes sense. Okay. All right. So now we have this matrix. So now we just, keep doing computations. So take the inverse of this. And then let's find this term here, right? So this term here is just I need to scroll up a little bit. And I dropped the transpose. Okay, so this here, right, will carry out over here, and I'll change the color to green. So, it's a separate computation. So x1 so this will just be, this summation here. I'll pick up the pace on the computations because it seems like you guys understand. Okay, so you get this summation down here. So we put it together, right? Putting these two together, we get this. Back to yellow. Actually, I'll erase this. So we therefore get inverse. Okay, so do you guys know the determinate trick for inverting matrices? Type yes in the chat if you do. Otherwise, I will go over it. Yeah. So, okay. So there's a formula for inverting matrices. For 2 by 2, it's this, right? So let's say I have a matrix. We'll call it A. And then so A11, okay. A1, actually, let me change color. White, okay. So let's say A equals A11, 1, 2, A21, A22. Then its inverse, we can use the determinant trick. In that we have A11, A22 minus A12, A21. Let's see. Is it? Let's see. Let me Wikipedia this real quick, because yeah. Always forget how to rearrange the. Yeah, so, yep. Okay, so we get A22, A11, negative. All right, so we get that. So for this matrix, right, we can use this trick to kind of get our solution. So we get AB. So using trick, we get okay. I'm gonna be lazy here. Sorry. Okay. So using trick, we get something that looks like that, right? And then we matrix multiply this out, which at this point, you guys probably get the point. So we can matrix multiply this out, like just using the regular row column thing to get this. Okay. So that's the answer after doing all the computations. It's just this. And if we check on Wikipedia, it's the right answer. Yeah. There's also a trick too, for more than 2 by 2. So if the matrix is larger than 2 by 2, well, yeah, you can probably look it up on Wikipedia, but yeah, then you have to do all this like fancy stuff with minors, and yeah, the formula is kind of long, but yeah. Okay, so that's the first part of the question. And then the second part of the question just asks you to use this formula to compute the coefficients. So part 2 of question 1 asks you to compute A comma B for actually I'll write a note here. Okay. So we have AVG is 8, RMS Y is equal to 13, AVG Y is equal to 12, and then AVG of okay. So I think the first thing you should do in this problem is to break down what each of this means. So basically, AVG, right, of x, right, is equal to this. And we know that this is equal to 8, and then RMS x is equal to square root 1 over n. Right. And like this and this is by definition, right? Just by definition of the root mean square and the average. And then for this one, it might be a little more complicated to see. But essentially what it's asking for is this. Right. So this is here, right? So from there, you can plug in this stuff into here, right? So we see from our formula that that this so there are certain terms that we can see here, right? So this right here is n times average of x, right? This is n times average of, right? And so on and so forth, right? So we can kind of plug in everything into here. Oh, and this is RMS x squared, right? So we can compute our coefficients just by plugging it back in, right? So does that make sense to everyone? Type yes if okay, that makes sense. Yeah. And I think for the sake of time, I don't think me doing algebra will be too useful. But after slogging through some algebra, you get a is equal to 1/9 and b is equal to 100 over 9. And so you can like check this when you go through the process yourself. All right. And then the very last question. So the very last question asks you to, or the very last part, compute compute mean squared error. So what is the formula for mean squared error? The formula for mean squared error is as follows. Right. So yeah, so basically root mean squared error is basically intuitively how different is the best fit line from the points of data, right? So our best fit line, right? So our data points, they're yi, and our best fit gives axi plus b, right? So the difference is just that, right? And then we take the square of that difference, and then we take the average of that. So that's mean squared error. And for this, you just do the computation. Yeah, not too much to explain there. But once you do the computation, it's R. So R wait. So MSE is equal to. So I made a mistake on my exam when I did it. So I computed the root mean square error, which is basically you take the square root of the MSE. So that's why I report 4.99 squared, because that's what I wrote on my exam. I wrote 4.99 on my exam for root mean square error because I misread the question. But yeah. Yeah, make sure you read the question correctly. All right, does this entire process make sense? Type yes in the chat if it does. Also, if I'm going too slow or too fast, just let me know. I can always adjust my pace. All right, I'm just gonna move on then. Question 2. So question 2 asks you to do the following. So part A, we have a symmetric matrix A. And then we have U is an n by 1 vector. So it looks something like this. U1, comma, UN. And then alpha is a real valued scalar. Oh, wait, 1 by 1. Yeah, I think that's all right. No, that's not, it's not right. Right. So, and then we were given this matrix. So H hat. So what this question is asking us to find is once condition on H and constraint for alpha such that in terms only H and U to make H hat positive definite. So does everyone understand what this question is asking? Give a react with a thumbs up if you understand. Okay. So how do you approach this question? So what makes a matrix positive definite? What is the definition? Does anyone know? Can anyone type it in the chat? What is the definition for a matrix to be positive definite? Yeah, that's correct. Alex is correct. It is x transpose hx has to be greater than or equal to 0 for any x. So let's write that down. Okay. All right. So there's also an equivalent condition though. So this is uh, so this is by definition, right? Um, but we can prove an equivalence case. So there's something known in the business called the Schur complement. And in this case, the Schur complement in this case is alpha minus U transpose H inverse U. So we have the condition that the Schur complement is positive definite if and only if the Schur complement of a matrix A is positive definite if and only if A is right. And the formula for Schur complement, I'm pretty sure is listed on the slides. And since this is an online exam, you can probably access the slides, is what I'm assuming. So yeah. Otherwise, just have it on your cheat sheet if that's what's allowed. Um, so this has to be true. Since, and we also know that this is a scalar, right? Then since that's a scalar, it suffices that alpha minus U transpose U is greater than or is greater than 0. Also for positive definite, this equality isn't here. So x transpose hx is greater than or equal to 0. This is semi. For positive definite, it's strictly greater than. Small correction. So yeah, so we need this to be true, right? Since we need the Schur complement to be positive. So alpha has to be greater than U transpose H and 1U. So we have also need to have that H is invertible, right? Otherwise, like this is bogus. Right? So therefore, we have our two conditions. Oh yeah, and then since we can also pick this to be arbitrarily small, um, so also note that alpha can be arbitrarily small. So we need right, right. So that implies that H is also positive definite, because because we have that. It implies that. So we obtain the following two conditions. Which is positive definite. Right, because and also invertible, because we know that positive definite implies invertibility. And then the second condition is that alpha has to be greater than U transpose. Right. Does that process make sense to everyone? Did I lose everyone, or does that all make sense? Give a thumbs up if it makes sense. I'm not okay. I am seeing one thumbs up from Jeffrey. So if no one else has any questions, I am going to assume that this is good. Okay. So we have solved the first part. Oh, I also provided a proof, I guess, in my problem that if H inverse is positive definite, if H is, I don't think you need to do that. Okay. But if you guys are interested, do you guys would you like me to go over the proof that if H is positive definite, then its inverse is as well, or no? Okay. Let me go over the proof. All right. All right. So, okay, let's prove this lemma. Proof. So H has positive eigenvalues since x transpose x is greater than 0 for all um x, right? So right, so this has to be true, right? So all x that are eigenvalues of H have to satisfy that, which means that we can do this. We can write that x transpose H x is equal to x transpose lambda x, right, is greater than 0, right? Because of the property of eigenvectors, right? So h, put this to the side. Let's see, h x equals to lambda x for right. So that has to be true, which implies that we can move stuff around to get this. Right, which this has to imply that this is greater than 0, since this must be greater than 0, right? Okay, and then we know that that since h is diagonalizable, right? We don't have any 0 eigenvalues, meaning that h doesn't have a kernel, right? Meaning that it is invertible. So also equal to 1 over lambda, right? And we can just see that because of the following. So if we have h diagonal, then we have lambdas, lambda 1, lambda n, and then its inverse will just be like 1 over, right? And then we have like the similarity matrices, right? Cancel, you get identity, and then you just get identity all the way across, right? That makes sense. Right. All right. And since it implies that 1 over lambda is 0, right? And so since H inverse has all positive eigenvalues, we can make this claim. Right, since right, these two combine to make that statement. And then we get all right. Does that make sense to everyone? So that completes the proof. Give a thumbs up if this proof made sense. All right, cool. Moving on. All right, so now we have B. B basically is this problem. And under what conditions okay. So by definition, we also see that this has to be true, right? Rn and C has to be in Rn. So that all has to be true. Okay, so when does this happen? So we can trivially see that right. So basically the question is asking like when can we find an X in this, right? When does X exist? Right. That's basically what the question is asking. So basically this is trivial, right? If it's inverse, then X will exist, right? So question to ask is when is M1, when is M invertible? Right. So let's visualize what M looks like. Okay, so that's kind of what it looks like, right? Along the diagonal, it's 1 plus AI BI. And along the rows, it's you know, A I for the ith row, and then times BJ for the jth column for I not equal J. So okay, so basically we know from linear algebra that M is invertible if the kernel is empty, right? So when is the kernel empty? Um, so we want so basically, so when does M have non-empty? So that will happen when mx is equal to 0x, right? So eigenvalue of 0, right? So if AB transpose x is equal to negative x, right? Then we get that AB transpose 1 plus identity plus AB transpose x is equal to 0, right? Does that track? Okay, so I'll move on. So therefore, AB transpose cannot have an eigenvalue of -1. So that's the condition for invertible M. Um, So, okay, so if we do the matrix multiplication for each row, so we get something that looks like this. If you recall what the thing looks like. So we have mx. So I'll expand x, right? Because we see that we have m here. Um, all right, and then so we have that, and which means that we get this. J 0, right? And so, right, right. So we can factor this out to get xi for each row, right? So let's factor it out. So we get ai j is equal to 0, which means that for this to be true, right? For this to be true only for xi equals 0, we must have -1, right? So we can also find the following relation. So let's look at A B transpose B is equal to A transpose, and so we see that so therefore so yeah, I don't know if that makes sense though. How do I explain this? Okay, so we can write it like this. So this is can be written as AI times the vector b times transpose with that is equal to -1. Um, and then let's see. So this gives All right. So we have that. So we can multiply this both sides by b. Right. So we get and then yeah. You can look at a bunch of algebra from this point, I think. But yeah, the main point is that you work all this out and you eventually see that A and B cannot be anti-parallel unit vectors. Yeah, I'm not going to play around with it now. Yeah, I'll post this on YouTube. Okay. All right. Third question. So the third question is you have a matrix that looks like this. So AK is that and invertible. And then for K between 1 and n, C is in, and then D is Rn minus K. All right. Oh, transport down. No, it's not what it wants. So we wish to prove this. So we wish to show that. And we want to show that, and we want to answer the following question. Is M unique? So is there only one matrix M that satisfies this? So we can do it this way. Let us just simply perform a matrix multiplication. So simply perform a matrix multiplication. So we get this. This. See? Okay. So we get the following relation. right? From looking at this and that, which means that M is equal to C, A, K inverse. And we also know that so M is unique, right? So we know that a matrix is square when it has a right and left inverse. And so when it's square, yeah, there's only one inverse. Okay. And then part B of this question. Okay. So we want to find the expression for d hat in terms of, oh, I forgot the hat. All right, so b hat, d hat. Okay, so find the expression for d hat in terms of these variables, right? So yeah, that's quite trivial because we low-key already have the answer. We just plug this in. So that's a boring question. I mean, it's 3 points. So, I guess for you guys, hopefully he puts a lot of questions like these on the exam. So that's just the answer. um, all right. So, and then we move on to part C. So this is LU decomposition. LU decomp of A and F. Okay, so we're given that A is equal to AK, B, C, D in the problem, right? Given. So what is the formula for LU decomposition? So for LU decomposition, the main idea is to get lower triangle matrix times an upper triangular matrix. Right. And using the formula for LU decomposition, we can find this. D prime. Right. So this gives us our lower and upper triangular matrix. So doing some matrix multiplication, you can find this. Our D prime is equal to D minus MB. So we can rewrite it like this. So that's our answer. So you literally just use the definition of Lu decomposition. All right. Next one. All right. So this is a minimization problem. Subject. Average is equal to 1 by n. Transpose x equals 1. So this is one vector. And that's just the definition of average in terms of, yeah. Okay, so also given. Okay, so what's the first question? So what they want you to do is that the first part A is they want you to argue that this problem is a constrained LS problem in the following form. And you need to specify A, B, C, and D. All right. Lowercase. All right. So so how many of you guys are familiar with Cholesky factorization? Okay, I'll write down Cholesky factorization. All right, so Cholesky factorization is like this. So suppose we have some matrix Cholesky. So suppose matrix A, then we can factor, actually, I'll write matrix B. Right, suppose matrix B, then its Cholesky factorization can be written B is equal to a transpose A, right? So we want to get it into this form. Why? Because pseudo inverses are nice. So we can write the matrix A like this. So, B11, we have B1, 2, N, and then we have B, uh, 2, 1, and then we have right. So we have, B in some form like this. So this is just the first one, and we got 1, comma 2, and let's put 2. Right, and then we have this this formula here. So this is where like most of the number crunching is. All right. So basically, you're gonna have to solve this to recover this term here. And basically, Cholesky factorization is that A is upper, right? So we have A in this one. Zero, and then right. So that's the main point of Cholesky. So it's a way of getting an LU factorization for a matrix. Okay. So how does this help us solve our problem at all? So if you recall here, we have this problem here. So let me rewrite what we wish to minimize. Um, Squared. Okay, so this is what we wish to minimize, right? So suppose we can factorize the right by Cholesky. Then where A transpose A is Cholesky factorization of B. And why do we wish to do this? So so for a least squares problem, we have something that looks like we have something that looks like this, right? Ax minus b squared, right? So if we notice that if we can get it into some form like this, right? X transpose so solving these problems sometimes requires a little bit of reverse engineering. So we want to get some form like this, right? So this is the same thing as ax minus b transpose, right? Ax minus b, right? So we can factor the transpose to get something like this, right? X transpose A transpose minus B transpose, right? Ax minus B. So doing that, we can get something that looks like this. Right? And there's a nice trick that we can do now is, we can let this happen. So pick b is equal to square root of lambda x, right? Now, when we plug it in, then we get something that looks like this. Uh, lambda x squared, right? And, we know that Cholesky factorization, it is symmetric. And by the symmetry, we can see the following. Oh, sorry, I'm a little tired. This is part of the session. Okay, so X transpose A transpose so we know that's 0. So we can write right, and then we sub this in. To get this, sub this in here. Two. And then we can, did I forget a factor of 2? Might have. And there might be a factor of 2 that I missed somewhere up there. But anyway, the point is that you can now factor this out. The point is now you can factor this out, and you can say that this is equal to ax minus root squared. Oh, yeah. There's some minus signs that went somewhere. But anyways, the point is that you start with something like this. So this becomes X transpose A X squared. And then you can add and subtract the same thing. So let's see. This goes to 0. And I've tried the same thing. And then from here, you can invoke the symmetry of Cholesky to get this. Wow. Central. I think I messed up a sign somewhere. This should be negative. I think. And then you can get this. Right. And that's just the process. Yeah. So like the main idea was just to find a way to factor out X transpose A transpose, right? So you can get just the singular A with the X. That makes sense. That is everyone. I'm sorry. So it's kind of hard to explain my thought process sometimes when doing these problems. Yeah, so yeah, that's the main point. So Cholesky factorization, yeah, let me redo part of the problem. So basically, if you just look at the form plus lambda squared, this is what we wish to minimize. These squares problems look like this, right? Which is equal to x. Say, what was it? Just real quickly. So, all right. So you have something that looks like this, and wait, this should be BA. This is a transpose. Okay. Okay, so you have something that looks like that, right? So if you compare these two, compare. So I'm gonna write down to 1 and 2, right? Compare 1 with 2, right? What are some differences? So let's say we can split. right? So let's say we can split B equals A transpose A, right? That gives us one step closer to 2. Right. So what we're missing is these middle terms here, right? So how can we get those middle terms? How can we get those middle terms to equal 0? Well, the answer is Cholesky factorization, because Cholesky factorization has the following property, where we have that's B transpose AX is equal to negative XA T, right? And that's, I think it's because Cholesky factorization is skew symmetric. It produces a matrix that is skew symmetric. And so because of this symmetry, so we have the property B equals A transpose A for A Cholesky means A is skew symmetric by construction. And this means that skew symmetry is just A is equal to negative A transpose, right? So that's what skew symmetry means. And so from this skew symmetry, we can see that this is true, right? So because that is true, we can substitute in like something that looks like this, yeah. X transpose A plus B transpose AX minus B transpose AX and X squared, right? And then we can use, the formula. So this becomes negative X transpose A plus B. And then you can kind of see there, right? So we pick B is equal to square root X, and we can get in the form that we want. Does that make sense? I can write it out explicitly. Right. So erase this. X transpose. So and that just gives us the answer. So yeah, that's how we need to use Cholesky factorization is, there's two things that one, we need to get, some form of like A transpose A to like factor stuff out. And then the second thing is that we need to some type of skew symmetry of A to cancel terms, like the middle terms in the FOIL, if that makes sense. So thumbs up if that makes sense. Did I lose everyone? Okay. Key topics. I'd say just do problems. And then like when you're doing the problems, like refer to the notes. Um, some of Vandenberg's additional problems are pretty good. Maybe some of the ones that you didn't do that aren't programming. Um, yeah. Probably the HK on YouTube channel. Yeah. I guess there's one more thing I can probably go over before the meeting's over. Actually, do I want to go over KKT? You can probably just look up the definition, but anyway, the if you want to solve the minimization problem given um by something that looks like this, is you can write down a Kkt matrix. So this part is just B. This is just one. And then this is something known as a right, and CC is another matrix two that you need to define. But yeah, it will look something like this. It'll be in your note. I think it's in your notes somewhere, and then just do the matrix math to get the solution. Yeah. Yeah, I think that's really all I have. The last problem is that on my final was something on the Hessian matrix, and the complexity for computing that. But I think I'm also out of time. So yeah. Are there any last questions? We did not have coding questions for our final. It was simply just a lot of linear algebra. Yeah. All right, I'm gonna end the recording here.